Okay, Gregor, first, thank you for your invitation. And of course, I'm pleased to present my, I have to say, beloved LIDAR data. I was thinking how to present LIDAR data and LIDAR itself and LIDAR data to so-called uninitiated public. Could be quite a big problem. So I decided that we will, instead of starting with all definitions and other stuff, to dig down directly to fly into the point cloud. So I'll show you what the point cloud looks like. So this is I have to zoom it in. So I hope that you see my screen. And here in the left window, we can see the whole point cloud. Of course, this is just one file of a larger project. And we can drive in or descend into the point cloud. And we see that this is all pointalized. So this is presentation of reality with points. In art, it's called pointillism, I guess. But here we talk about point clouds. So if we rotate a little bit in the 3D, we can observe features of the real world, like cars, buildings. I guess that here is one street lamp, something like that, wires, many objects. Of course, these points have a color, but they can be presented also in some other ways. Let's see their elevation, maybe. Yeah, it will be an ugly one, so I will not show that. Let's see their class. So each point can also have a class that it belongs to as an object. So we can see that cars are orange here. This traffic light or the street light is light blue. Cyan, some other objects. Vegetation here is dark green. So this is one of the property of the point cloud, one of attributes. So each point can have a class. There are many other attributes. I will list them later in my presentation. And we can also do some neat things with this point cloud. Of course, we can make here a cross section. Maybe you can see my mouse, and I will make a section view through this street light with depth. And it will be shown here in this right view here. I have to remove, okay. So where is the street lamp now? God knows where. Oh, that's another one. Probably I moved something. Yeah. Oh, that's strange. Anyway, yeah, it's that's the problem. Let's do a big one. So this is completely 3D data. Completely 3D data. We can rotate it. We can do special analysis with this data, and it provides a geometry of the real world at the time of when we acquire this data. Okay, I will jump back into my presentation. So now we kind of see what the point cloud actually is, or LIDAR data actually are. So this was the live demo. From LIDAR data, we can produce many products. One of the most common, and probably some of you have, is a digital elevation model. This is gridded data, where the grid values are the mean sea level heights, so the ground heights. As you can see here, I made a nice presentation, so there is a little bit shadow. The blue one is the lowest value. whether reddish color is highest value. I guess from my read, this is around 100 meters above sea level, and this one here is approximately 150. On the same area with the same LIDAR data, so previous slide was I present a terrain model, is normalized digital surface model. Yeah, this is a long word, but what actually is the height of each object. So these three, so the highest objects in this area are those trees because they're reddish. So the lowest value, or 0, probably is the blue one. And the highest value is the red one, and all in between are there. So this gridded raster data presents height of those objects from the ground. Okay, so the next one, the LIDAR data products are very suitable for archaeology because the LIDAR, let's say, penetrates canopy, so three canopies, not completely, not like a radar, but it can penetrate, and we can observe features on the surface that are quite subtle, but still we can observe that. And in this case, we can see there is a forest area. We can see nothing there, but from the ground data, from the LIDAR data that was classified and ground was extracted, we can observe some features that could be potentially interesting to explore. Of course, cultural heritage preservation it's also widely used. LIDAR is also widely used in this cultural heritage preservation to monitor the state of heritage and to prevent or to be able to restore an object if some kind of disaster occurs. Right? So here we have one temple, I think it's somewhere in East Asia, which was scanned from outside and from inside. It's in complete 3D form. So they can practically, I would say, rebuild it, yeah, okay, with the help of this LIDAR data. Forestry is also one of earliest and main usage of LIDAR products. Here we can see an image. This is an orthophoto, but still positions of trees were extracted from LIDAR data and some properties of those trees. As tree height, we can also extract canopy boundary. We can also extract volume, approximate volume of the tree mass, and we can also predict danger or what kind of, if there is a forest fire, what is the energy will be released. Let's go. Energy sector also quite use a lot of LIDAR data. Here is the image of analysis for energy potential of the roofs in this area. As you may see, some roofs are obstructed with a shadow from the trees. These are trees. These are roofs. So we can decide on which roof can we put, or it makes sense to put electrical those solar cells. The industry is also a large user of LIDAR data, especially in the processing facilities. Here I am showing you how the new process line or some part of the line is incorporated into existing infrastructure, and So it is used for planning. It's used also for asset management with the help of LIDAR data. We can extract 3D shapes and attach to those shapes, to those pipelines, to those devices that are in the processing plant. We can attach attributes like when the device was produced, who installed this, what is the date when it should be replaced or something like that. And we can also, with the help of LIDAR data, we can also help to plan how, if we have to put something inside this facility, let's say that some truck delivers some goods, or I don't know, if it's safe to go inside and what is the safety distance and stuff like that. So I would like to show you also the live demonstration of our data, LIDAR data. So here, as Gregor mentioned, I'm working a lot with the powerline inspection. In powerline inspection, we are scanning powerline and vicinity of the powerline to find where some kind of dangerous vegetation, so the trees that are too close to the power line, to the wires, if those trees could fall onto the wires, and also if there are some kind of buildings or new buildings in vicinity of the power line that are too close, of course. So we have here a power line, and with the help of LIDAR data, we made a nice presentation of this power line in vicinity. This is visualization of LIDAR data. You can see here a mast. The green is vegetation. The vegetation height is colorized. So dark green is lower vegetation, and more into the yellow colors, there's high vegetation. We also done a vectorization of buildings, of rooftops, because this is also kind of important information to have for our customer. And of course, we extract from LIDAR data 3D wires. So wires, where the wires are, what is their position. And then we extract also the 3 positions, maximums, and their heights. And of course, also 3 canopy polygons. And we made, the last is the analysis for this area. We made analysis so we can find some, I can show you some trees that are too close to the line. So this is one tree that is too close to the line. As you may see, it is 4.6 meters from the nearest wire. And there are also some trees that could fall to the, if they fall in the direction to the power line, they will be really close to the line, or even they will cut the line, the wire. And this is one result that our customers needs to maintain, to safely operate the power line. Okay, let's jump back. LIDAR data is more and more used. So the first users were, of course, state authorities like defense mapping and geodetic authorities, and later local authorities and power distributors. So those were the first who used LIDAR data. And the usage is really wide, and it is getting wider and wider. So it's used in the urban infrastructure planning, in mapping, asset management, in flood prediction and prediction. So from the ground models, we can make prediction of the flooding. So 100-year water, 1000-year water, stuff like that. And also in disaster management, so like fire, earthquake, and in response. Telecoms are also using LIDAR to planning networks, especially now 5G network is planned strictly with LIDAR data because it provides, you can analyze where the shadow will be of the signal from the 5G antenna. I mentioned culture and heritage preservation, forest management, and civil engineering. Interesting usage of LIDAR data is also part deformation and replication. So when some company that produce some parts want to verify if the part is a proper dimension, they can scan it with LIDAR, special LIDAR, and they can compare to the model. And this is also useful for replication. And of course, LIDAR will be used in future autonomous car driving, not in Tesla, but in other cars. So the usage is really wide. Okay, so the LIDAR data actually means LIDAR point cloud. And it is a representation of reality and provides geometry for this reality. We can also measure LIDAR point clouds. We can make analysis, we can make planning, we can detect objects. We can also detect changes if we have, imagine that we have one LIDAR point cloud scanned I don't know, last year, and we are scanned now, and we can then compare those LIDAR point clouds and to see what the changes are. And of course, for nice presentation, like mapping. And LIDAR enables us to doing that fast over large areas and with high accuracy. So, so what is LIDAR? LIDAR is abbreviation for light detection and ranging. It is an active sensor which is using pulsing laser beam. So the laser beam is emitted from the LIDAR scanner. It is kind of comparable to radar, but with less range, worse penetration, and the LIDAR has a better spatial resolution because it's using light, not other electromagnetic field. So most LIDAR has laser beams have a wavelength in near. That means it's not a visible spectrum of light. There are some that are in the visible spectrum of light, and that doesn't mean that they're not harmful. If you're looking too close into the LIDAR, you can go blind. That means like 2-3 meters. It depends on the power of the LIDAR. LIDAR data acquisition is called scanning, and it is quite complex endeavor. Remember this image here, because this is the emitting beam, laser beam. Here we have the first return, so the part of the light bounces back from the top of the tree, goes back to the LIDAR, and some part of this beam can go through, or let's say to the ground, and then goes again back to the LIDAR, and the LIDAR detects that. Okay, so how this works? So LIDAR scanner emits this laser beam pulse, and in known time, so the time is known when this pulse was emitted, and the direction the direction is also known. It's called scan angle. Then laser pulse hits an object, like, I don't know, rooftop or the top of the tree from previous slide, and the part of it reflects back to the scanner, and the scanner detects this. So this is called an echo. The distance is then calculated by the time difference between when the pulse was emitted and when the pulse was received back into the scanner. We know the the speed of light, right? And so we can distinguish that, we can calculate then the distance from the scanner to the target. The position of LiDAR scanner is provided, in this case, we have a plane, is provided with trajectory, so it's well known, and combine this trajectory and the scan angle and distance, we can calculate where we are. So this is really so then then we get the x, y, z coordinate of each point, of each target, of each echo. So this is basic principle. It's quite complex, of course, but it works. It's kind of a miracle, but it works. Let's go on. Yeah. So LiDAR point cloud can have several properties. The first and maybe the most important one is what kind of scanner we are using, and of course, what kind of features do we scan. So we have three classes here, three types. The first one is airborne. We already saw that in the previous slide. So it is done by plane or by helicopter, or nowadays also with UAVs, so with drones. It is top to down principle of scanning. So we are flying above our area, above our reality, and we scan down. It is suitable for scanning, of course, larger areas. And it is the oldest, I would say, the oldest principle of scanning. The second one is mobile. You can see that this van here on the right, it has LiDARs on the top of it. And with mobile, we can mount a LiDAR on a car, train, or we can even walk with it. So it is suitable for scanning roads, railways, and for autonomous driving. The third one is terrestrial, so it is fixed position. This is the one on the top right. So this LiDAR is in a fixed position, and it turns 360 degrees and scanning around itself, everything that is in the vicinity. It is suitable for smaller areas, inside buildings, also outside buildings, with vertical complex structures. And the smaller areas, of course. We can, of course, glue together many of these stationary scans into one large scan. So the other class of properties are point cloud density. We are talking here how many points per square meter are in the point cloud. This varies quite a lot. So in our case, when we are scanning larger areas, this can vary from, I don't know, 2 points per square meter in old times to several hundred points per square meter nowadays, in some smaller areas, of course. The terrestrial scanner or point cloud data has a resolution, I don't know, 10,000 points per square meter. The third property is coordinate resolution. In the case of a real scanning, laser scanning, it doesn't make sense to have coordinates, I don't know, with millimeter or even better resolution, because the accuracy of the data is described in centimeters. But in the case of terrestrial, yeah, you can have in microns, maybe, or millimeters at least. The date of scanning is also important, especially in aerial scanning. When we're scanning in, let's say, in the early spring or in the late autumn, when there are no leaves on the trees, the LiDAR scanner will penetrate, the light will penetrate all these branches, there are no leaves, and we will have a lot more points on the ground or near the ground than if we scan in the high summer when the leaves are on. And of course, georeferencing information like coordinate system is also important. So here is the list of the points in the point cloud. So each line we present one point, and we can see there's a lot, we can put a lot attributes to each point. Of course, mandatory ones are X, Y, Z, so position, time of acquisition, intensity, reflectance, so how much of the pulse gets back, what is intensity. There is also number of the echo and how wide or was this echo. So we are calling those the raw, because these are raw attributes. They cannot be recalculated later, right? This is raw LiDAR data, and then the calculated attributes of each point cloud, like class. You can see here is the visualization of the classes, then color of the point, distance from the point. In this case, the distance from the ground to each point to the ground, and many more attributes can be calculated. So the LiDAR data is quite big. In this case, we have to divide the area. As example, we have in one project here, we have 700 square kilometers with 80 to 100 points per square meter. We divided that into 6,000 tiles, 500 by 500, and the final cloud point size was 3 terabytes, and the raw point cloud size was 1.5 terabytes with all the colors and attributes. So let's go on to the format. Most usable format nowadays is LAS. This is also the oldest one. It is well supported. The governing body is American Society for Photogrammetry and Remote Sensing. It's an open format. It is a binary one. And it supports large number of standard point attributes, but can also be extended with some additional ones. The latest version is 2 years old. It is well maintained and well documented. The other one is my favorite one. It is the most used compressed LiDAR data format. It is lossless compression. It is lossless compression, so we don't we get all the data as it was in a compressed form. It was developed with Martin Eisenberg from Germany. It is an open source format, and again, it supports additional attributes, and it supports also coverage of the files, which is kind of important to know where the files are positioned. The last one is, of course, ASCII. Is the simplest format and the most customizable one. It is human readable, but I wouldn't suggest to read this table to read this data that way, because it's really a large one. It is really slow to write and read, and it takes a lot of space. So I made a short analysis of those three formats. What are the sizes of those? I've used LiDAR data with a color, and the LiDAR data has 36.6 million points, and they were colorized. And here are the numbers. As we see that LAS is 1.3 gigabyte, LAS zip is 0.2, and ASCII is the largest, 2.7 gigabytes. So it takes a lot of space. What it means for the LiDAR data preservation, well, there are some challenges. The first one is there is a big amount of data. But in the future, I think that this challenge will kind of diminish, because the disks, the storage capabilities are growing. The LiDAR formats are also developed quite fast. There is a lot of development in LiDAR. In LiDAR, there are new attributes added. We want those attributes to be standardized, so they're added into the formats. and the LiDAR application is growing really fast, especially with autonomous driving. It was skyrocketing. But of course, probably those data would not be available to the public. Then one challenge is also that storage of point clouds or LiDAR data is migrating to the web with a new web-friendly formats or web-friendly structural formats. That means that we can extract, that we can read the whole area really fast to see where the area is, to see, observe, to preview. But then we can also read each point, also if we get in closer and closer. And of course, non-LiDAR point cloud data is more and more present. This point cloud data is made by photogrammetry. So when we have a lot of images of the same object, we can put them into the computer, and the computer will calculate will find same points on the each image, and will extract the coordinates from those. So the questions are: what is the most suitable format for preservation? What to preserve? Is the raw LiDAR data or just final point cloud data? And which point cloud attributes are to be preserved? And this is the question for you. For users, what they would like to preserve, in what kind of form, and how much data it will take to preserve this. Okay, thank you very much. If there are some questions, I would really like to answer them.
Thank you, Lojze. It took a little longer, but it was very interesting, so we enjoyed listening to this. So
yeah, I would talk a whole week.
Yeah. So are there any questions for Lojze regarding LiDAR data? And
yes, I have one question.
Yes.
Good morning, Tom from Netherlands. You're saying the file size is getting quite big, but I'm curious about the durability of the common LiDAR formats, because I think LiDAR is already here for a pretty long time, like say 20 years or maybe longer. I'm not sure. What are the odds that you can read a 20-year-old LiDAR file with the common applications we use today?
Great question. I would say, as my experience is, I would say all of them. Because let's talk about LAS format, which is the most prevalent one. It is kind of backward compatible, so you can read it without the problems. The problem is that, as I see, is that custom attributes that are added into, let's say, one customer wants to have, I don't know, to store the height of each point from the ground. This attribute is not stored as a standard attribute in LAS or LAS zip even, and that means that we have to kind of put additional attribute into the LAS, and the customer can then read this LAS, but it is not the part of the standard format. So this is something that should be sorted out with metadata. So this LiDAR data set, which can cover a whole country, has, of course, X, Y, Z, intensity, those standard attributes, But in metadata should be stated, yeah, it has also additional attribute, and that is, let's say, the height from the ground. Yes. And this is something that is, but if you read this data without knowing that there is some additional data there, it will be completely fine. So the standard part of the and then you will recalculate, of course. So these are those recalculated attributes that can be reprocessed, recalculated, and this is something that is this is the real question, because the methods in the future, I guess, it's of calculating this with this deep learning and artificial intelligence and all those buzzwords, they will get better and better and more accurate. So it is a question, if I want, as a customer, let's say if I want to pick up, I want to get LIDAR data 15 years old, and I would like to make some kind of comparison, right, with the newest one. I'm doing now this. If I have all the data, I recalculate those and get newer attributes. If of course the processing was not on the level that I demand now, right?
Yes. So if I understand correctly, the LIDAR data, if you make it standard, the raw data is pretty durable, but the calculated data you have to recalculate maybe later in future.
Maybe later, but you should be aware of the cost of it, of course.
Yes.
Because and when we are talking about raw data, this is not the data directly from the LiDAR scanner. So this is the data that is already georeferenced. So it has all the properties of the point cloud. So X, Y, Z coordinates and everything else.
Yes. Yes, because the answer for what should be preserved, that should be context, but that should also be the thing which is the most durable, which you can reuse. So that was my thinking on your question on the last page.
Yeah, thank you. For me, this is archiving and preservation is completely new field of view, and it is nice to have this point, to see on the data from this kind of point of view. Really great. It helps a lot.